Hey, this is Mr. Mitchell with another video. One of the things we're talking about in this video is the difference between the word accuracy and the word precision. As people who collect data for experiments and observations, you naturally want to be both accurate and you want to be precise. However, there is a slight difference between the two, and we have a diagram below to hopefully help you understand. If you take a look where you have here, you have a bullseye and you have the target has been hit lots of times, but only once right in the middle, and none of them very close to each other. If they were all together, they would have been more precise. They would have had a high amount of precision. They would have more precision if they were all together. This does not have much precision. This is low precision. They are hit all over the place, and they happen to be very low accuracy too. If a lot of them had hit the bullseye like here or here, then you would have had a much more accurate shot. See, accuracy is getting it right. Accuracy is the extent to which a value is true, the extent to which you have it right. Precision means precise, which is not always accurate. Precision is the degree of exactness in measurement. Here you have high precision, you just happen not to be accurate. Here you have high precision and accuracy. Here you have high accuracy. A lot of them are around the bullseye, but not as precise as they are here and there. Hopefully that helps a little bit right there. Another thing I want to talk to you about in this video is something called literal equations. There will be times in this class and in life in general whenever you have a formula, but the information you have doesn't seem to fit the formula just right. Here, if you have the data for what F, which is force, it's 25 newtons, and the data for what the mass is, 100 kilograms, look here. You have something that you don't have, and you have to solve for that. So if you were to just plug this data in, it wouldn't seem to work out very well. However, there is a way to solve for A. Solving for A, you do it like this. You write the formula that is the existing formula out. So I will go F equals m times A. What I want to do is to get this A on one side by itself. Right now it's not. It has the m with it. So anything you do to one side, you have to do to the other. So I'm going to figure out how I can get this m out of here. And the way I can get it out of here is divide it by m. Let's say this m is 1. Divide by 1. Say it's 12. Divide by 12. And it cancels out. And you're left with A. Now, like I said, anything you do to one side of the equal marks, you have to do to the other. So since I have divided this side by m, I also have to divide this side by m to keep it equal. So this m cancels out with this m, so you are left with A on this side. So you have A, and flip it over. You can flip the equation over because it is equal. A equals force over mass. So A is the acceleration, by the way. So here you can plug in the force and plug in the mass, and you have solved for A. So that's how you do a literal equation when you need something that's multiplied like this. But what if you have a division problem? Let's try to solve for D first of all. So if I have velocity, which is what V is displacement over time. How can I get this D alone on this side? It has to be isolated on one side. What can I do to the whole side? Well, what I can do is multiply by T. Because what happens, this is like 1 over T times D. So you have to have something that cancels the t out. And by multiplying both sides by t, I'll put times t on this side, that will get the t out of this side. So you multiplied t on this side and multiplied t on the other side. So you are left with d, and now you are able to flip the equation, equals v times t, velocity times time. And that will give you the displacement, or distance in many cases. So that's how you do that whenever you are dividing something. Ooh, what about this one? We have a lot of these problems here, but a lot of these terms, but I just now noticed that we did not solve for t, which is what I asked for down here. Now, if you solve for t, that's something you cannot possibly complete in one, just multiplying it by t. Now, how would you get this off of this side? Now, I'm sure there may be a way that a mathematician might know more than I would, but what I would do is I would at least get both sides multiplied by t, just like I did before, to get to where it's in a more manageable state. And whenever I did this before, t's canceled out, and I ended up with that. So at this point, how would I get t by itself? Now this is a lot like the one up top. You would divide this side by v, and then that would get rid of the v's would cancel out. So what you then do to one side, you have to do to the other. So I will cancel these out, and t equals d over v. I will put way over here. Oops, my bad. T equals displacement over velocity. So that's what you would have there. What about here where you solve for VF? This is the acceleration formula. This is final velocity minus initial velocity over time. What are we going to do here? Well, I'll just use this written part as the first step. We would attempt to get VF all alone on one side. So in order to do that, let's do a couple of different steps. Let's multiply both sides by t. So in doing that, that cancels out the t's, and you're left with VF minus VI equals AT. I think I will write that down. VF minus VI equals AT. Let me go with a different color just because this is looking pretty muddled here. Okay, this is A and this is T. So I'm trying to get VF on one side. What would you do to just have VF on this side to get rid of the minus VI? You can add VI to both sides. So if I add a VI to this side and I add a VI to this side, then that should do it. VF minus VI plus VI, the VI's cancel out. Think about this. If VI were 5 minus 5, that would be 0. But you'd have to do the same thing to the other side. So you finally have VF equals, that's not very good, equal AT plus VI. Right there. I know it's a little muddled right up here, but that's how you would go about doing that. Now let's take a look. You can tell this is kind of a video where I put a lot of things in here together. We went from accuracy and precision to literal equations to some lab safety rules. Now, when you have lab safety, hopefully your lab would not look anything like this. I think the artist just tried to get as many bad things possible to have happen in one place. But let's go over some simple lab safety rules. One is take responsibility. The lab is not the place to play pranks. It's not the place for throwing things whatsoever. It is a place to take responsibility. You can see this person here is doing what they're supposed to do, and then somebody's coming up and pushing her. That's bad, bad, bad idea for a lab setting. Number 2, read or hear instructions first. Don't just dive in and start mixing things and tinkering things. That's a bad idea whenever it comes to the things you would use in a science lab. No eating, drinking, or putting on makeup or chewing gum whenever it comes time to being in the lab. No unauthorized experiments. If you are finished with an experiment, don't suddenly think, hey, what if I mix this and this together? I'll do this. And you kind of need to get permission to do that, because whoever is in charge or the teacher might know what would go together and what wouldn't, and what would be the right thing to do. Number 5, don't remove the equipment. Don't just take stuff from a lab, whether it's the lab in my classroom or any lab. You don't just take stuff. Wear safety goggles. Now, there are some times when you would not need to wear goggles, but your teacher would know in any given experiment if goggles are the thing to wear. Number 7, report all spills or accidents. It may be something harmless, but it may be something that needs urgent attention. Don't know if you can see this very well with the purple background, but it says no long hair or clothing. Sure, you can have long hair, but you better put it up whenever you're handling things in the lab. Also, you can see open-toed shoes and sandals are a bad idea. And naturally, loose clothing like, well, this guy is wearing here is probably not a good idea as well. Oh, let's see where we got to. No location of safety equipment and exits. Now, one of the things we have in our lab is going to be a sink. It's pretty obvious where it is and where the exit is, but in all labs it might not be as obvious, and there may be some more safety equipment. Avoid inhaling fumes. Most fumes will not hurt you, but you do not want to be the one to find out the hard way that a certain fume will damage your lungs. Number 11, use bulbs for pipettes. Believe it or not, this is what a pipette looks like. And years ago, people used to suck in on the pipette to get the water or other liquid in the pipette. That's not a good idea unless it's water, and it's still not a good idea just for the habit's sake of not sucking water up in a pipette. You have these little, I guess you'd say, ends of the pipettes where you can squeeze on them, and that will get the water, or more than likely some material besides water, where it should be. So do not do that. Number 12, watch out for hot glass. What happens is glass will heat up and it doesn't show signs of heating up. The liquid inside can be very, very hot, or the solid inside can be very, very hot. And if you just reach and touch it, you might be in for a bad surprise and break the glass and hurt yourself. During a fire drill, not fire equipment, but during a fire drill, you do need to turn off any equipment that is turned on already. Number 14, leave your books at your desk. And the last few. Common sense tells you, number 15, clean up when you are done, whether it is something that hurts people or not hurts people, or something that is a danger, you still need to clean up, even if it's simple just water, or if it's simple dust or something, you do need to clean up. And finally, the sinks in a lab, a science lab, are not for trash. Trash goes elsewhere. The sinks are for liquid and for rinsing and for getting the water that you might need. I know this has been kind of a hodgepodge of a video, but I hope you have learned a little bit about accuracy and precision, literal equations, and lab safety.